Hello, so this project is on brain tumor MRI classification using Ensemble Deep Learning by me, Mahrouj Kamran, and Sabitur Maharaj. Brain tumors are a serious medical condition where accurate and timely diagnosis is critical for treatment. However, manual interpretation of MRI scans is time-consuming and inconsistent. The main goal of this project was to develop a deep learning-based image classification system capable of categorizing brain MRI scans into 4 different classes. The objective is to explore transfer learning using pre-trained CNNs and combining models through ensemble learning to achieve high performance and accuracy. This project is important in the computer vision field as it explores modern model architectures and helps analyze how pre-trained CNNs and ensemble models can transfer to other fields, such as medical images. So the dataset. We used a publicly available brain tumor MRI dataset from Kaggle consisting of 7,023 images collected from multiple sources, as mentioned. So these are our 4 classes, which are split into training and testing sets, and the trained data is further split into training and validation subsets with a 25-75 split. So during pre-processing, we standardized the inputs. All images were resized to 224 by 224, converted to RGB and normalized. During training, we applied data augmentation such as small rotations, flips, and brightness adjustments to improve generalization and avoid overfitting. There are some limitations to the dataset as it consists of 2D MRI slices rather than full 3D volumes. This limits spatial and contextual information, potentially reducing diagnostic accuracy. Moreover, the dataset is small compared to large-scale computer vision datasets, which can limit the model's ability to generalize to unseen clinical cases. Also, since the dataset combines MRI scans from different sources and scanners, the model may associate specific patterns with tumor labels, introducing domain bias. So for the training procedure, training was performed using PyTorch in a Jupyter Notebook environment with using GPU acceleration when available. First, we trained ResNet and EfficientNet separately in 2 stages. In stage 1, the pre-trained backbones were frozen and only the classifier heads were trained for 8 epochs with a small learning rate of 10 to the -3. And in stage 2, deeper layers of the models were unfrozen and fine-tuned with early stopping and using an even lower learning rate to allow the models to adapt to MRI-specific patterns. Then we got the best models for both from the epochs with the highest validation accuracy. We combine these to form an ensemble model whose predictions are obtained by averaging the class probability outputs of the best models. For our hyperparameters, our optimizer was Atom. We used cross-entropy loss, fat size of 32, and we used a learning rate scheduler with a patience of 2 and factor of 0.5. To reduce overfitting, we used dropout of 0.4 on the classifier heads and implemented early stopping at 3 epochs. We also used data augmentation to reduce overfitting, as I had mentioned before. So our model architecture. Our model is an ensemble model that uses transfer learning with 2 complementary pre-trained CNN architectures, ResNet-50 and EfficientNet-B0. First is ResNet-50, which is chosen for its deep residual network capable of learning complex visual representations without the vanishing gradient problem. Second is EfficientNet-B0, which was chosen because it is more parameter efficient with a balanced scaling while maintaining strong performance. For both models, the original ImageNet classifier was replaced with a custom classification head tailored for our tumor classes. Here's a representation of the training procedures I described earlier on the models to create our ensemble model. So for evaluation, we evaluated the models using test accuracy and loss metrics on our held-out test set. So here are the accuracies and losses. ResNet-50 achieved 98.7 accuracy, EfficientNet-B0 achieved 95.42 accuracy. The Ensemble model with test and augmentation achieved the highest accuracy of 98.86, which is comparable to and in some cases slightly higher than some of the recent CNN-based approaches for brain tumor MRI classification, which had reported accuracies ranging from approximately 97 to 99.2. Here you can see our qualitative visual example cases. So these are showing the MRI scans with the ground truth and predicted label. These examples demonstrate some of our correct and stable predictions across different tumor types and the model confidence levels for them. So from a computer vision perspective, our results highlight the effectiveness of transfer learning for adapting pre-trained models to specialized domains like medical imaging. Moreover, we can see how ensemble methods help to improve accuracy by reducing model-specific errors. Our ensemble model accuracy of 98.86 is comparable to recent reported results from other ResNet, EfficientNet, and GoogleNet-based transfer learning models and studies, which report accuracies ranging from 97.35 to 99.2. Future work could extend this approach to 3D MRI volumes, datasets, and validate performance on larger clinical datasets to further improve generalization and clinical trust. Here are references, and thank you for listening.